Okay, good morning, everyone. Before we start, just wanted to make sure that you are able to see the screen. Can someone please confirm?
Yes, sir. Screen share.
Thank you. Thank you very much. So we're going to start and do a little bit of recap of what we did in the last two lectures. Started with the continuous random variables, and we talked about the probability density function, which answers all the probability questions about a random variable, about a continuous random variable. So just like for the discrete case, we had the probability mass function. For the continuous case, we have the probability density function. So for the discrete case, we have the probability mass function. Similarly, for the continuous case, we have the probability density function. And both of these, they tell us everything about the random variable. There is another function which is called the cumulative distribution function, or CDF. So this one is your PMF, and this guy is your PDF. So there is the CDF, which tells us what is the accumulation of the probability mass function or probability density function for both discrete and continuous case. For both discrete and continuous case, cumulative distribution function has the same form, which is probability x less than equal to x. Probability mass function tells you what is the probability x takes a value equal to x. Probability density function does not tell you this. It does not tell you, just like discrete case, what's the probability x takes the specific value, because that value is always 0. Instead, probability density function, it tells you that what is the probability that you are over an interval. This random variable is over an interval a to b. This is the probability that the random variable is between the interval a and b. Okay. Then we had a few examples of random variables, continuous random variables. And the first one that we saw was uniform random variable. And as the name shows, uniform random variable. And as the name shows, this guy has a uniform density function. Uniform means constant density function over an interval a to b. And the height of this function is 1 over b minus a. And the reason is it is 1 over b minus a is because the probability density function must integrate from minus infinity to plus infinity, must integrate to 1. So this area under the curve has to be equal to 1. So इसकी height जो है वो 1 over b minus a. Okay. Now, the expected value for the uniform density is, expected value is a plus b over 2, the midway between the a and b guy. The median is also the same. Okay. And the variance of x, which is uniformly distributed over a and b, from a to b, it's uniformly distributed, is b minus a whole square over 12. This is something that we saw last time. And there is a special case. Special case was uniform over 0 and 1, which of course will have an expected value of 1 over 2 and a variance of 1 over 12. B को 1 डाल दें और A को 0 डाल दें. This density function which is shown here, this is uniform, generic uniform from A to B. Then we had an example of exponential random variable. Exponential random variable. And the exponential random variable had a density function given by lambda e to the minus lambda x. While the uniform density function has two parameters a and b से define होती है. So exponential random variable is defined by just one single parameter, lambda, which is here, which appears here. And the shape of this density function looks like the following. Okay. Goes all the way to infinity. Okay. And the CDF for CDF capital Fx of x is given by 1 minus e to the minus lambda x. Also for lambda, you can see. Class, you have a question?
No, sir. Sorry.
कोई बात नहीं. And the CDF looks like the following. The CDF looks like the following. इस तरह की उसकी shape. Okay. And we found the expected value of the exponential random variable as 1 over lambda. इसकी जो expected value थी, this was 1 over lambda. And the variance for the exponential random variable was 1 over lambda squared. So uniform and then exponential. And then we also talked about the memoryless property of the exponential random variable. Memoryless property of exponential. And we related this memoryless property of the exponential random variable with the memoryless property of the geometric random variable. In the discrete case, geometric random variable is the number of tosses you need until the first success. ठीक है. और अगर हम आपको पहले बता दें कि 5 tosses पहले ही हो गई हैं और अभी तक success नहीं आई है, given this information, you are standing at the at square one. Okay. You are, you know, if I tell you that the first 5 experiments, first 5 tosses are a failure, अभी success नहीं आई है, तो उसके बाद scratch से start हो रहा है सब कुछ. जो next toss कर रहे हैं वो बिल्कुल scratch से start हो रहा है, कोई information आपको नहीं मिलती. So that's why it's called memoryless. Similarly, for exponential random variable, if I tell you कि lifetime of a bulb is exponential random variable, so given that it has run already for 2 years, what is the expected lifetime? वो same ही रहेगा, constant ही रहेगा, वो 1 over lambda ही रहेगा हमेशा. Then there was another extension of exponential random variable. We defined exponential random variable as a useful random variable for modeling situations until something happens, until a success appears, time until a success appears. And then we defined the more generic gamma random variable. Gamma random variable, which is the time until 3 successes appear or 4 successes appear or alpha successes appear. And the expected value for the gamma random variable was n over lambda. N over lambda or alpha over lambda. We use the parameter alpha actually. So I'm going to use alpha here, alpha over lambda. And the density function of the gamma random variable was the same as exponential with some additional things, which was lambda x power alpha minus 1 over gamma function of alpha. Now, we also connected the Poisson distribution with exponential and gamma. So if the arrivals are Poisson, remember Poisson random variable was a discrete random variable. Poisson random variable was a discrete random variable. And one example that we did for Poisson random variables is if you are reading a book, how many typos you will see on a page. एक page पे कितने typos होंगे? Very small probability that you will see a typo. and very, very large number of trials. So binomial with large number of trials and small probability of success in each trial, that would model the Poisson random variable. So Poisson random variable में, if I tell you कि until time t आपके पास कितनी successes आ गई, which means कि कितने typos आपके पास आ गए. So that will be gamma random variable. पहली टाइपो तक जितना टाइम लगेगा, that's an exponential random variable. पहली टाइपो के बाद दूसरे टाइपो तक जितना टाइम लगेगा, that's another exponential random variable. So many of these exponential random variables added together, ये सारे exponential random variables हैं added together, ये जो टाइम आपके पास लग रहा है, so कितना टाइम टोटल यहाँ से यहाँ तक लगेगा, this would be gamma random variable. This is one manifestation of the gamma random variable. And then we talked about the normal random variable, which is one of the most important naturally occurring kind of random variable, also called Gaussian random variable. And the density function is the standard bell curve that we see with a mean of mu and variance of sigma square. Variance tells you the extent of thickness of the curve, of the bell curve. अगर variance ज़्यादा होगी तो thickness ज़्यादा होगी, which means कि random variable will tend to take values far away from the mean. अगर bell ज़्यादा हो. So what this curve tells us is basically कि what is the probability your random variable takes a value between this point and this point. So it's this probability. A और B के बीच में, what is the probability that your random variable falls between A and B? That's given by this red area. So probability your random variable, which has a PDF given by this, falls between A and B, and it doesn't matter whether it is less than, equal to, or less than, falls between A and B. This is given by this red area. ये वाला red area. Okay. So the probability density function of the normal random variable was 1 over square root 2 pi under root sigma e to the minus x minus mu square over 2 sigma square. And of course, there is a special case for this guy as well. And the special case is fxx is equal to 1 over square root 2 pi. Sigma is 1, mu is 0. Sigma is 1, mu is 0, e to the minus x squared by 2. Sigma is 1 and mu is 0. So standard deviation or the variance, both are 1 and the mean is 0. This is called a standard normal random variable. इसकी शेप कैसी होगी? इसकी भी शेप वैसी होगी. इसकी भी शेप वैसी होगी, except that it is centered on the mean, which is 0, and the extent here is 1. The variance is 1. The shape is figure में देख नहीं सकते, but the variance is 1. So this is your standard normal random variable. Normally we use capital Z to denote the standard normal random variable. Now, in order to answer the probability question about a random variable which is normally distributed, so to answer this type of a probability question, what is the probability A is less than X is less than B? Is this red area? तो ये red area हम कैसे निकालेंगे? Red area ऐसे निकालेंगे कि ये probability density function है आपके पास fx of x, इसको integrate करते हैं a to b. Turns out the integral is not very easy, is not very friendly. So उसके लिए tables मौजूद होते हैं, but you cannot provide table for all values of mu and sigma. So you provide tables for the standard normal random variable. Tables for z, which is normal 0, 1. But how do we answer questions about x, which is a normal random variable with a generic mean mu and generic variance sigma square? उसके बारे में हम सवाल कैसे आंसर करेंगे? उसके बारे में सवाल आंसर करने के लिए we need to move a transformation between x and z. So if x is normal with mean mu and variance sigma square, this is the notation that we use. So there is a relationship between x and z, and the relationship between x and z is z is x minus mu. X में से mu minus कर दें. So x is the random variable, z is also the random variable, mu is a constant, and divide by the standard deviation. Then x and z are interrelated if they are normally distributed, with z being the standard normal and x being a generic normal with mean mu and variance sigma square. And then we did an example in which we answered a probability question about x. The probability x less than 3.5 कैसे करेंगे? टेबल से डायरेक्ट x को देख नहीं सकते. x की मीन और वेरिएंस अगर आपके पास स्टैंडर्ड नहीं है, so you standardize x and then you get the answer from the standard normal table. वहां से आप आंसर निकालते. Now the CDF of z is equal to fz of small z is equal to CDF क्या होता है? Probability that z takes a value less than equal to z. So z taking a value less than equal to z is, let's say you have small z here. So this probability z less than equal to z is the area to the left of this guy z. ये पूरा का पूरा एरिया इसके लेफ्ट पे जो है, ये रेड एरिया जो मैं शेडेड कर रहा हूँ, this entire area all the way to minus infinity, this area is probability z less than equal to z. ये fz of z को अक्सर डिनोट करते हैं phi of z से भी. सेम थिंग, दो डिफरेंट नोटेशन है. अक्सर बुक्स में जो है वो phi of z लिखा हो. Phi of z, same thing. So this is also equal to phi of z. So phi of z is basically this red area which is shown in the figure. And when you see the tables, you will normally see phi of z listed for positive values of z. Z की सिर्फ positive values के लिए होता है, but z की negative values भी तो हो सकती हैं. उसके लिए कैसे जवाब देंगे? So if you have minus z here, which is some value where z is positive, minus z is negative, how do you find the area to the left of this? ये जो blue वाला shaded area आ रहा है, इस area को कैसे find out करेंगे? Well, realize that normal distribution is a symmetric distribution around the mean. Zero के left पे और right पे ये symmetric है. So this blue area must be the same as this green area. Which means that phi of minus z, which is the blue area, is the same as 1 minus phi of z, which is total area minus red area, which means the green area. देखिए, रेड एंड ग्रीन दोनों को ऐड करेंगे अगर, तो आपके पास आंसर 1 आएगा, because this is a PDF. Okay. So phi of minus z, which is the blue area, is the same as 1 minus the red area, which is the green area. Okay. 1 minus red area is the green area. So that's how you would be able to find, the value of phi for negative value. So that's how you read the CDF of the standard normal random variable. These tables are generally available to you. Okay. So I'm going to ask this question: what is phi of 0? Phi of 0. Answers in the chat window. Phi of 0. Phi of 0. 0.5. 0.5, of course. And phi of infinity is, answers in the chat window. Phi of infinity is 1. And what about phi of minus infinity? It has to be 0. Okay. phi of minus infinity has to be 0. Okay, and we have a couple of examples in the class notes. Kindly take a look at that. Kindly take a look at that. So I'm going to cover a very, very important example now. And this example is about signal detection. Signal detection. What do we mean by signal detection? So you have a sender here, and a receiver here. Maybe you are sending something over the wireless channel. यहाँ से कोई चीज भेजी और यहाँ पे भेज दी. ठीक है? Normally, when the sender sends something to this receiver, these days you will send the data in the digital format. Data आप भेज रहे होते हैं in the binary digital format. So you will send two symbols, +1 or -1. यहाँ से +1 और -1 भेजेंगे. ठीक है? So maybe you can think of this as +1 means कि आपने +50 वोल्ट का एक सिग्नल भेज दिया और -1 means कि -50 वोल्ट का सिग्नल भेज दिया. ये भी हो सकता है +1 का मतलब है कि आपने +5 वोल्ट भेज दिया और -1 का मतलब है 0 वोल्ट भेज दिया. So how it is sent, it's none of our business in this course, at least. So what we are going to consider is that we are sending these binary symbols. Okay? So we are sending +1 or -1, +1 or -1, one after the other, one after the other. Each time you send one of these symbols, you can consider these to be bits representing the bits which collectively will make a big file. एक फाइल आपने अगर कहीं पे ट्रांसफर करनी है वो भी इसी तरह जाती है. आप डिजिटाइज करते हैं और डिजिटाइज करने के बाद 1010 को भेज देते हैं. वो 1010 भी ऐसे ही है, +1 और -1. It's just a two different representations of that. So when you send these symbol, it would not have been a problem at the receiver if the channel between the sender and the receiver, is perfect. कि जो भेज दिया वही मिल गया. यहाँ से मैंने 5 वोल्ट भेज दिए तो 5 वोल्ट मिल गए, 3 वोल्ट भेज दिए तो 3 वोल्ट मिल गए. पर ऐसा होता नहीं है. What you send from here, उसके साथ रास्ते में एक noise add हो जाता है. Noise added, and this noise which is added is naturally occurring noise, and naturally occurring noise is typically modeled as a normal random variable. So यहाँ से आपने सिग्नल भेजा, सेंडर ने सिग्नल भेजा S, रिसीवर ने रिसीव किया Y. Ideally I would want Y to be equal to S, because Y पे आपने डिसाइड करना है कि +1 भेजा था या -1 भेजा था. So when you send +1, Y should receive +1. When you send -1, Y should receive -1. Ideally. But we know that it's not ideal. But you receive instead Y is equal to your S plus this noise gets added. And this noise is modeled as normally distributed with zero mean and variance sigma square. We'll see that sigma square tells you about the power of the noise. High variance means high noise. Low variance means low noise. देखें, वेरिएंस अगर जीरो हो जाए तो इसका मतलब है नॉइज जीरो है. क्यों? उसका मीन ही जीरो है. तो दैट मीन्स कि एवरी टाइम you sample the noise, every time you look at the noise, you will always get the zero value. But if the variance of noise is large, which means कि ये बड़ा fat सा curve है, if the variance of noise is large, every time you take a look at the noise, यहाँ पे आपका n है small n, every time you take a look at the noise, you will observe a value which may be very far away from the mean. वेरिएंस पे डिपेंड करता है. वेरिएंस जितनी ज्यादा होगी उतनी ज्यादा प्रोबेबिलिटी है कि you will see some value far away from the mean. Now, when this noise gets added, the receiver is not going to receive what the sender has sent. So the receiver has to make a decision. रिसीवर ने क्या डिसीजन करना है? रिसीवर ने ये डिसीजन करना है कि या +1 भेजा गया था या -1 भेजा गया था. ठीक है, मोस्ट ऑफ द टाइम द रिसीवर विल डू a decent job. जो भेजा गया था उसको ही गेस कर लेगा. सो फॉर एग्जांपल इफ यू सेंड अ 1 और उसमें थोड़ा सा नॉइज ऐड हो जाता है, 1.1 हो जाता है, ठीक है, द रिसीवर विल स्टिल से ओ 1.1 तो एग्जिस्ट ही नहीं करता, सेंडर कभी भेज ही नहीं सकता, सेंडर सिर्फ +1 भेज सकता है या -1 भेज सकता है. सो इफ द रिसीवर रिसीव्स 1.1 प्लस 1.1, वो डिसाइड करेगा कि जी ये +1 भेजा गया. If the receiver receives -0.7, what should the receiver decide? -0.7, what should the receiver decide? The receiver should decide कि sender ने -1 भेजा था. Why? Because -0.7 is closer to -1 as compared to +1. ठीक है, so ये +1 और -1 के बीच में अगर आप देखें तो 0 आता है. 0 से बड़ी अगर कोई चीज मिल गई तो रिसीवर डिसाइड करेगा कि +1 भेजा गया था, 0 से छोटी कोई चीज मिली तो वो डिसाइड करेगा कि -1 भेजा गया. ठीक है, this works very well most of the time, but one fine day it would happen that the noise is so large, कि आपने -1 भेजा था, और नॉइज उसके अंदर 2.3 का नॉइज ऐड हो गया, तो आपको रिसीवर के ऊपर मिल गया 1.3 और रिसीवर ने जो है वो गलती से फिर डिसाइड कर दिया कि +1 भेजा गया था. So that's a mistake that the receiver will make. This is called an error. This is an error that the receiver has made. There are two ways you can make an error at the receivers. One is you send a +1 and the receiver decides by looking at whatever is received, receiver decides that -1 was sent mistakenly, erroneously. The other way that you can cause an error, two ways that lead to error. First is that you send +1, the noise got added, the receiver received something and decided -1 was sent. That's an error. And the other is you send a -1 and you decide a +1. Let's try to find the probability of error in each of those cases. By symmetry, you should appreciate that both of these will be equal. ये और ये equally आएंगे. Why they are equal? Because of the symmetry. ये नॉइज जो है जितना पॉजिटिव हो सकता है उतना ही नेगेटिव भी हो सकता है. It's a symmetric distribution around 0. अगर नॉइज का मीन 0 ना होता, फिर these two answers would have been different. But let's try to find out what are the errors in each of those cases. So don't forget that y is s plus n. N is normally distributed with mean 0 and variance sigma square. What is the PDF of y? What is the distribution of y? What is the density function of y? What kind of a random variable y is? Okay. Well, it's very hard to answer that generically without knowing s. Okay. However, if I tell you if s is equal to +1, if s is equal to +1, so this is a condition which is given to you. This should limit your sample space. Okay. If s is +1 given to you, then y is simply 1 plus n. And what is the distribution? Of y? So Vikas has asked the question, in case of 0, what will you decide? Well, you can toss the coin at that time. 0 अगर आपको मिल जाए तो coin toss कर लें, और head आए तो +1 कह दें और tail आए तो -1 कह दें. And the probability of that happening, the probability that noise will take a value of +1 or -1 is 0. What is the distribution of y? देखें, आपके पास एक normal random variable है and you added 1 to each of those values. It's simply a shift of this distribution. ये जो noise की distribution थी ये वाली, एक्सेप्ट कि इसका मीन जो है 1 पे चला गया. Expected value of y is going to be 1 plus expected value of n, which is equal to 1 plus 0, which is 1. And variance of y is going to be the same as variance of n, which is sigma squared. Now I have not rigorously shown that the density function of y is also normal density function, but it can be easily shown. Y is obtained by adding +1 to noise. So noise is normally distributed. +1 एक add कर देंगे तो distribution disturb नहीं होती है. It will still remain normal distribution, except that the mean has been shifted to +1. So this distribution is a normal distribution. With mean 1 and variance sigma square. And this distribution is conditional PDF. We will talk a lot more about conditional PDF in the next class. Conditional PDF of y given s is equal to +1. Similarly, there will be another conditional PDF of y given s is equal to -1. वो क्या होगा? वो भी normal distribution होगी, but वो -1 पे centered होगी. So probability of error given s is equal to +1 is the probability that you decide कि -1 सेट किया. Probability you decide that -1 was sent. When do we decide that -1 was sent? You decide that -1 was sent when y is less than 0. You decide that -1 was sent when y is less than 0. And this is the distribution of y. This is the conditional distribution of y given s is equal to +1. So यहाँ पे कहीं 0 आएगा, यहाँ पे कहीं 2 आएगा. So this is the probability of error. So अब देखें कि अगर noise की variance कम होती, this sigma square was small, तो ये कर्व जो है ये बहुत थिन होता. तो ये probability of error जो ये blue shade से यहाँ पे दिखाई गई है, this would have been very very small if the variance was small. And this makes sense. ये जो हमने पहले कहा था कि variance जो है noise की power बताती है. अगर noise की power कम हो जाए, variance कम हो जाए, sigma square कम हो जाए, तो probability of error भी कम होगी. Now let me just find that out कि ये है क्या. So probability of error when s is +1, this is conditional probability of error. Okay. Similarly, there will be a probability of error when s is equal to -1. जब s is equal to +1 है तब भी error हो सकती है. S is equal to -1 हो. Similarly, we can find कि तब क्या error होती है. So this is equal to the probability that y is less than 0 given s is equal to +1. But given s is equal to +1, the conditional PDF of y is this normal distribution with mean 1 and variance sigma square. So this is equal to the probability that s plus n, which is y, your received signal y is signal sent plus the noise, is less than 0 given s is equal to +1. So this is equal to the probability n is less than -1. N is less than -1 given s is equal to +1. Normally, the noise and the signal, they are independent of each other, which means कि noise की जो distribution है वो तो naturally occurring है. उसकी सेहत पे कोई फर्क नहीं पड़ता कि आपने सिग्नल 1 भेजा था या -1 भेजा था. Noise तो उसकी वही distribution रहेगी. So this would be probability noise is less than -1. But noise has a distribution which is normal 0 and sigma square. इसको कन्वर्ट करते हैं probability noise -0 over sigma. Normalize क्यों किया? So that you get this guy is standard normal distribution. Why? Mean minus करें, उसकी standard deviation से divide करें, तो you will get this z guy which is normal 0 1. ऐसा क्यों करने की जरूरत पड़ी? इसलिए जरूरत पड़ी कि हमारे पास नॉइज के टेबल्स नहीं है, नॉइज के टेबल्स नहीं है विद 0 एंड सिग्मा स्क्वायर, उसके टेबल नहीं है, 0 और 1 के साथ टेबल्स हैं हमारे पास, ठीक है. सो दिस शुड बी लेस देन -1 over sigma, -1 over sigma, which is equal to the probability that your standard normal z is less than 1 over -1 over sigma, -1 over sigma, which is the CDF, phi of -1 over sigma, which is 1 minus phi of 1 over sigma. ये भी आपको बताया था कि phi of minus z और phi of z जो है वो कैसे related होते हैं. Okay. Similarly, you can find that probability of error given s is equal to -1. ये क्या होगी? ये भी इसी के बराबर होगी by symmetry. 1 minus phi of 1 over sigma. इस केस में चूंकि सिमेट्री थी तो यही आंसर आएगा आपके पास. So overall probability of error, which means कि you send a symbol, एक symbol आपने भेजा +1 या -1 and then you made an error. हमें नहीं पता कि आपने +1 भेजा था या -1 भेजा. You made an error whatever symbol you sent. So probability of error PE, probability of error is equal to probability that you make an error given s is equal to +1 into the probability s is equal to +1 plus the probability of error, law of total probability लगाया, s is equal to -1 into the probability s is equal to -1, law of total probability. Okay. So this is equal to probability of error given s is equal to +1 is 1 minus phi of 1 over sigma. And what is the probability s is equal to +1? Well, this depends upon what is the mix of binary bits that you are sending. उस bits जो आप भेज रहे हैं वो 0 1 कितनी है? 50% 0 है, 50% 1 है. Normally that is the case. So this would be 1 over 2 and this will be 1 minus phi of 1 over sigma also multiplied by 1 over 2, which turns out to be 1 minus phi of 1 over sigma. This is your probability of error. Notice that when sigma is large, then phi of 1 over sigma is going to be, when sigma is large, then you will have phi of 1 over sigma to be small, phi of 1 over sigma to be small. Which means phi of 1 over sigma small हो जाएगा, so probability of error large हो जाएगी. So large sigma will lead to large probability of error. And this also makes sense considering कि हमने sigma को बताया था कि this is the power of the noise. If the noise power is higher, then there is a higher probability that you will make an error. Okay. So normal distribution is extremely important, and one of the things that I'm going to tell you now is one of the two major results in the probability theory. One of the two major results. In fact, दोनों अभी बता सकते हैं आपको. So two major results in probability theory. One is the law of large numbers. There are two versions of this. One is weak law of large numbers and the other is strong law of large numbers. So law of large numbers क्या कहते हैं कि if you repeat an experiment a large number of times and there is an underlying random variable, so उन experiments को perform करने के बाद if you take the values, जो आपको values नजर आती हैं and take the mean of that, it will converge to the real mean of the distribution. Example देते हैं आपको कि so dice roll करते dice roll, and let's say I define x is the phase shown. So x can take values 1 2 3 4 5 6, ये 6 वैल्यूज ले सकते हैं. एक्सपेक्टेड वैल्यू ऑफ x क्या होगी? एक्सपेक्टेड वैल्यू ऑफ x होगी, इन सबको ऐड करें 21/6, so 3.5 एक्सपेक्टेड वैल्यू. लॉ ऑफ लार्ज नंबर ये कहता है कि एक डाइस को रोल करते जाएं आपके पास ये मुख्तलिफ नंबर आते जाएंगे. सो लेट्स से यू रोल्ड द डाइस 1000 टाइम्स. सो 1000 जो नंबर्स आए उन सबको एड अप करें, 1000 से डिवाइड करें, जो आपके पास उस सैंपल से जो मीन आएगा दैट विल कन्वर्ज टू दिस 3.5. So this is a non-rigorous a little bit of hand-wavy definition of the law of large numbers, but for now it suffices. The other major result in the probability theory, which is tied to the normal distribution, is called the central limit theorem. And the central limit theorem says that if you have a large number of random variables which are independent and identically distributed. You have random variable x1, x2, x3, ... which are independent of each other and also identically distributed. इन सब के डिस्ट्रीब्यूशन सेम है. डिस्ट्रीब्यूशन सेम होने का मतलब नहीं है कि रैंडम वेरिएबल्स सेम है, ये डिफरेंट रैंडम वेरिएबल्स हैं. ऐसा समझ लें कि आपने एक एक्सपेरिमेंट किया, रैंडम वेरिएबल जनरेट कर लिया, फिर एक्सपेरिमेंट किया, उसी डिस्ट्रीब्यूशन से एक दफा और रैंडम वेरिएबल जनरेट कर दिया. सो सेम थिंग एज सेइंग कि ये आपने जो डाइस रोल की थी, हर दफा आपको एक डिफरेंट नंबर आता है, हर दफा एक नया इंस्टेंस आपको मिलेगा, सो x1, x2, x3 could be the different instances from the same distribution. So these are IID, independent and identically distributed random variables. So अभी central limit theorem अभी आपको बताते हैं. उससे पहले let me just first ask you this question: what is going to be the expectation? Let's say expectation of xi is mu and variance of xi is sigma square. ये हमने आपको बता दिया कि for each of these xi, क्योंकि ये identically distributed हैं, same distribution से हैं, so हर एक का mean mu है, हर एक की variance जो है sigma square, and they are independent. Now the question is, what is the expected value of x1 plus x2 plus ... plus xn? Answers in the chat window. ये expected value क्या हो? Expectation linear होती है, हमें ये पता है. So the answer should be very simple. What is x1 plus x2 plus x3? उस sum की expected value क्या है? Anyone answers in the chat window? n times mu. And the variance of x1 plus x2 plus ... plus xn, this is going to be equal to, answers in the chat window. Any guesses? Well, this is n times sigma square, not n square times sigma square. क्यों? क्योंकि ये सारे इंडिपेंडेंट हैं. We can show this. ये किसी और टाइम पे हम शो भी कर देंगे इसको. So let's say I call this guy x1 plus x2 plus xe up to xn. इसको हम कहते हैं कि this is Sn, sum of these independent identically distributed random variables. Now ये तो साइड नोट थे. सेंट्रल लिमिट थ्योरम क्या कहता है? सेंट्रल लिमिट थ्योरम कहता है कि Sn is normal irrespective of the distribution of xi. When when n is large. अगर ये बहुत सारे रैंडम वेरिएबल इंडिपेंडेंट आइडेंटिकली डिस्ट्रीब्यूटेड, इन सबको आप ऐड कर लें, उस सम की जो डिस्ट्रीब्यूशन आती है वो नॉर्मल आती है. नाउ दिस इज वेरी सरप्राइजिंग. This is very very surprising. So what I am saying in essence is that कि आपके पास एक ये यूनिफॉर्म रैंडम वेरिएबल है, एक और यूनिफॉर्म रैंडम वेरिएबल लेकर आते हैं, उसकी भी डेंसिटी ऐसी होगी, एक और लेकर आते हैं उसकी भी ऐसे होगी. ठीक है. सो ये x1 है, ये x2 है, ये x3 है, ऑल आर द सेम. मैं इन सब को ऐड कर देता हूं, x1 plus x2 plus x3 plus x4 all the way up to xn. For a sufficiently large number, the distribution of the sum is going to be normal. Amazing result. This is an amazing result. x1 plus x2 plus dot 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 up to xn. For large n उसकी डिस्ट्रीब्यूशन ऐसी होगी. आपको ये दो के केस में बता देते हैं कि x1 plus x2 इसकी जो डिस्ट्रीब्यूशन होती है वो ट्रायंगल होती है. नाउ यू कैन सी कि ये ट्रायंगल हो गई, फिर तीसरी आएगी तो एजेस थोड़े से और गोल गोल हो जाएंगे, और फिर so on and so forth. And you will see that after adding sufficiently large number of uniform random variables, uniform जो बिल्कुल इस तरह बॉक्स कार किस्म की उसकी डिस्ट्रीब्यूशन है, after adding sufficient number of uniform random variables, you will see that the distribution of the sum, the PDF of the sum, will turn out to be looking very very normal लगेगा. So this is very interesting. This is very interesting. Which means that I can try to answer a large number of questions by simply using the normal distribution. अगर मुझे पता चल जाए कि underlying जो है वो is sum of many different random variables. So formally, so x1, x2 dot 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 up to xn is a sequence of IID random variables. IID random variables. Expected value of xi is mu, and variance of xi is sigma square for each of them. And they are independent, identically distributed. Then Sn has a distribution which is normal with the same mean as this guy. S is defined to be x1 plus x2 plus dot 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 up to xn. ये n of these, इनका जो sum है वो ऐसा है. For large n, Sn की जो distribution होगी would be, Sn का हमने mean पहले निकाल लिया है, n times mu, and the variance is n times sigma square. Which is very interesting. So what that also means कि अगर मैं Sn ले लूं, उसमें से n times mu minus कर दूं, and square root of n times sigma से divide कर दूं. What I have done here is, एक normal था मेरे पास, एक normal था, non-standard normal था, जिसकी ये mean था और ये variance थी, उसको मैंने normalize कर दिया, उसमें से उसका mean minus कर दिया, standard deviation से divide कर दिया. So this should tend to be equal to, should tend to be z random variable z, जिसका CDF हमें पता है कि हमें टेबल से भी मिल जाता है. So I can try to answer all the questions about Sn. Very simple example. Let's say you load 100 boxes on a plane. एक प्लेन के ऊपर 100 बॉक्सेस जो हैं वो आपने लोड कर दिए. Each box का weight has weight. Each box का weight is uniform between 5 to 50 pounds. 5 to 50 pounds. So what is the average weight? expected value of the box weight. Average weight कितना होगा? Answers in the chat window. Average weight 5 से 50 तक यूनिफॉर्म वेट है आपके पास. What would be the average weight? यूनिफॉर्म की एवरेज कैसे निकालते हैं? 5 plus 50 divided by 2. So this is going to be 27.5. So this is the average weight. ये आपने 100 बॉक्सेस इस तरह के जिनमें से एवरेज वेट हर एक का जो है ना वो 27.5 था. तो हम क्या एक्सपेक्ट करेंगे? हम एक्सपेक्ट करेंगे कि ऑन एवरेज जो है वो 2750 जो है 2750 पाउंड्स उसका एवरेज वेट हो. 2750. I am interested in the probability that total weight exceeds 3000 pounds. Total weight exceeds 3000 pounds. So basically, I'm interested in the probability that S100 is greater than 3000. But what is S100? S100 is sum of 100 uniforms, each between 5 and 50. Central limit theorem हमें क्या बता रहा है? Central limit theorem हमें बता रहा है कि sum of 100 uniforms, 100 is a large number here, is going to be a normal. ये एक normal होगा जिसका mean क्या होगा? जिसका mean होगा 2750, and the variance would be n times sigma square, which is going to be 100 times n times sigma square. Sigma कैसे निकालेंगे इसका? 50 minus 5 square divided by 12. And this turns out to be 2750, and this guy is 16875. ये इतनी variance होगी. So this is your S100. S100 is a normal random variable with this mean and this variance. So what is the probability this guy is greater than this? This is equal to 1 minus, it's easier to find this way. आप दूसरी तरह से भी find कर सकते हैं, कोई ऐसा मसला नहीं है. 1 minus probability of S100 is less than 3000. Is less than 3000. ये ऐसा क्यों किया? इसलिए किया कि ताकि अब मैं लिख सकता हूँ इसको. This would be equal to 1 minus probability of ये S100 minus 2750. S100 minus 2750 divided by square root of 16875. इसे divide करें. Is less than 3000 minus 2750, which is 250 divided by square root of 16875. ये क्या किया हमने? ये हमने standardization की. Standardization. So now this is turning out to be 1 minus probability Z is less than, and this number turns out to be 1.92, which is equal to 1 minus phi of 1.92. And then you can read phi of 1.92 from the table. The table देखते हैं. Table. Yeah. So we were interested in finding 1.92. So this is 1.9, and this is 1.90. This is 1.91, and this is 1.92. This is our guy, 0.9726. This is our guy, 0.9726. So this would be 1 minus 0.9726. 0.0274. सो यहाँ पे क्या किया कि 100 बॉक्सेस थे, हर एक का वेट यूनिफॉर्म था। 100 बॉक्सेस जो हैं उनके वेट को ऐड कर लिया हमने। उनके वेट को ऐड करने के बाद सेंट्रल लिमिट थ्योरम लगा दिया। सेंट्रल लिमिट थ्योरम हमें क्या कहा है, वो कहते हैं कि ये S100 जो है, विच इज द सम ऑफ द वेट ऑफ द 100 बॉक्सेस, वो 100 यूनिफॉर्म्स को आपने ऐड कर दिया, वो आपके पास नॉर्मल होगा। नॉर्मल होगा विद सम पैरामीटर्स, जो पैरामीटर्स होंगे उसके वो 100 टाइम्स द मीन ऑफ द यूनिफॉर्म, एंड वेरिएंस वुड बी 100 टाइम्स द वेरिएंस ऑफ दिस यूनिफॉर्म। सो ये आपके पास एक नॉर्मल रैंडम वेरिएबल आ गया विद सम मीन एंड सम वेरिएंस, और उसको हमने स्टैंडर्डाइज किया। स्टैंडर्डाइज करने के बाद टेबल से लुकअप करके आंसर निकाला। So very small probability कि the weight will exceed 3000 pounds. The weight will exceed 3000. हमें लग भी रहा था कि ये 2750 is the mean. 2750 is the mean. So there is another very interesting example of parts processing given in the notes. Please take a look at that. उसमें भी ये central limit theorem ही apply होगा. Now I'm going to talk about another approximation, another very useful. You can see that central limit theorem में ये आपने देखा कि बहुत ये मुश्किल क्वेश्चन था जिसको आंसर करना शायद बहुत मुश्किल हो जाता। 100 यूनिफॉर्म्स को उनकी डिस्ट्रीब्यूशंस को ऐड करना और फिर कैसे निकालेंगे उसकी डिस्ट्रीब्यूशन, नहीं निकाल सकते। बट सेंट्रल लिमिट थ्योरम ने जिंदगी आसान कर दी कि उसने कहा कि इफ देयर इज सफिशिएंटली लार्ज नंबर ऑफ यूनिफॉर्म रैंडम वेरिएबल्स देन द सम ऑफ दोस, उसकी डिस्ट्रीब्यूशन निकालने की जरूरत नहीं, बिकॉज सेंट्रल लिमिट थ्योरम ये कह रहे हैं कि दैट्स अ यूनिफॉर्म डिस्ट्रीब्यूशन, दैट्स अ नॉर्मल डिस्ट्रीब्यूशन, दैट्स अ नॉर्मल डिस्ट्रीब्यूशन। So now I'm going to talk about the Gaussian or normal approximation to binomial. If you recall, binomial was if you have n tosses, the number of successes in n trials. Okay. So binomial को हमने ये भी कहा था, binomial is equal to sum of many Bernoullis. Bernoulli is the probability of success, it's one when you have a success in a single trial. एक single trial करें with some probability of success. If you get 1, then the Bernoulli will get a value of 1. If you get 0, the Bernoulli will get a value of 0. So binomial is simply the sum of all those successes, which is the sum of all those Bernoulli random variables. But if n is large, then the sum of Bernoullis, sum of large number of Bernoullis, ये तो हमारे पास नॉर्मल होना चाहिए, So यहां पे हमें ऐसे लग रहा है कि ये बाइनोमियल है, जिसको हम कहते हैं कि number of successes in n trials. In fact, both of those are true, and the reason for that is कि binomial, for a large number of n, the binomial starts looking like a normal. जैसे जैसे n increase होता जाता है वो normal distribution की तरह का लगना शुरू हो जाता है. So the shape of the binomial distribution, अगर आप binomial probabilities को draw करें, वो इस तरह की आ रही होती है. इस तरह. So there is a sort of an envelope here. The envelope here. Compare this with the continuous distribution. ये normal है. Now there is another caveat कि binomial is discrete. Binomial is discrete. ये तो specific values लेता है, 1 success या 2 success या 3 success, and normal is continuous. तो ये दोनों को हम comparison कैसे करते हैं? Well, the shape looks similar, and the probability questions about the binomial can be answered by using the normal. So the claim is कि if Sn is the number of successes, is binomial in n trials, is binomial with mean n times p and the variance n times p into 1 minus p. इस n times p को हम म्यू कह देते हैं, n times p 1 minus p. ये बाइनोमियल के मीन और वेरिएंस हैं, ये हमने निकाले हुए डिस्क्रीट के केस में, इसको हम सिग्मा स्क्वायर कह देते हैं. So Sn is binomial mu and sigma square. Sn can be approximated by normal mu and sigma square, the same mu and same sigma square. उससे approximate कर सकते हैं. What that means is कि Sn minus mu over sigma approximated by normal 0 1, standard normal. मीन को माइनस कर दिया उसका और वे उसकी स्टैंडर्ड डेविएशन से डिवाइड कर दिया. So that's approximated by normal 0 1. So binomial again discrete है, normal is continuous, तो probabilities को कुछ थोड़ा adjust करना पड़ेगा. What we mean by that is कि example से show करते हैं. कि let's say कि you have a binomial random variable. Sn is a binomial random variable with parameters 36 and variance which is 0.5. Variance 0.5. Find the probability Sn is less than equal to 21. ये हम मालूम कर सकते हैं, हमें पता है बाइनोमियल की कैसे प्रोबेबिलिटीज कैलकुलेट करती है, बट ये बहुत सारी कंप्यूटेशंस होंगी, यहाँ पे बहुत सारी कंप्यूटेशन होंगी. सो प्रोबेबिलिटी Sn is less than equal to 21, हम बाइनोमियल प्रोबेबिलिटीज कर सकते हैं कि k is equal to 0 to 21, ऐड कर दें 36 choose k, 0.5 power k, 1 minus 0.5, which is the probability success, is 36 minus k, n minus k. In ये binomial probability है, binomial probability को 0 से 21 तक हमने ऐड कर दिया. So that will give you the probability Sn less than equal to 1. This is the accurate answer. And if you compute this, this answer turns out to be 0.8785. By the way, binomial is discrete, so it makes a difference if you have a less than equal to or less than here. Continuous के केस में हमने देखा था कोई फर्क नहीं पड़ता, लेकिन discrete के केस में ये फर्क पड़ जाता है. So if we do a normal approximation, yeah, consider in normal with the same mean and the same variance, okay, and try to find probability Sn, इसको हम Sn कह देते हैं, less than equal to 21. So this would be equal to phi of so Sn में से उसका मीन माइनस करें और फिर Sn minus mean divided by square root of 0.5. इसके साथ आप डिवाइड करें. So this would be equal to 21 minus 36 divided by the square root of 0.5, which was the variance here. Well, ये तो आंसर आ जाएगा इसका, and this will give you some value. अभी आपको बताते हैं वो क्या वैल्यू आएगी. But यहाँ पे before we answer this, एक क्वेश्चन और आता है कि what if somebody asks this question, probability Sn less than 21? We know, okay, since this is binomial, this is not going to be equal to the probability Sn is less than 21. क्यों? क्योंकि उसमें Sn taking the value 21 उसको हमने निकाल दिया, तो फिर ये समेशन जो है ये 21 के बजाय हमारे पास ये 20 तक होनी चाहिए थी. ये समेशन जो है ये हमारे पास 21 की बजाय 20 तक होनी चाहिए थी, अगर लेस देन 21 होता था, ठीक है। लेकिन नॉर्मल के केस में तो वो एक ही आंसर आ जाता है। वेल, सिंस दैट द आंसर हैव टू बी डिफरेंट, आंसर्स हैव टू बी डिफरेंट, तो मुझे यहाँ पे कंटिन्यूटी करेक्शन करनी पड़ती है, कंटिन्यूटी करेक्शन करनी पड़ती है। तो यहाँ पे मुझे क्या करना पड़ेगा, यहाँ पे मुझे कुछ ऐड करना पड़ेगा, यहाँ पे मुझे कुछ ऐड करना पड़ जाएगा। सो व्हाट आई विल डू इज कि binomial takes the value is the number of successes. So I'm interested in 21 less than equal to 21. So 21, 22, 20. So I take the midway. I take the midway और ये 0.5 उधर ऐड कर देते हैं, 0.5 इधर ऐड कर देते हैं. And if you calculate this probability, this is phi of this guy, टेबल से लुकअप करें तो इसका आंसर आता है 0.8785, which is exactly the same as this. इतनी अच्छी approximation, इतनी अच्छी approximation. So I'm going to ask this question: what about probability Sn taking a value 19? Taking a value 19. We know that for continuous case this should be 0. Normal का केस में ये 0 होनी चाहिए, लेकिन binomial के केस में ये 0 नहीं होती. हमें पता है binomial के केस में ये 0 नहीं होती. इसको कैसे approximate करेंगे? इसको approximate करें, approximate with probability Sn takes a value between 18.5 and 19.5, and this Sn is normal with mean mu and variance sigma square. इससे approximate करेंगे. So this is called the continuity correction. This is called the continuity correction. The continuity correction. In the notes there are some situations which are given. जहां पे आपको ये पता चलेगा कि ये बाइनोमियल की जो अप्रोक्सीमेशन है नॉर्मल से, why it is very useful. बहुत सारी कैलकुलेशंस अवॉइड कर देती है, बेशुमार कैलकुलेशंस आपकी बची. Finally, I'm going to talk about the function of random variable. We already had a brief discussion about this function of a random variable. So you have a random variable x and y is a function of x. Y is a function of x. Y is g of x. You know the PDF of x. Find PDF of y. PDF or CDF of y. So very easy, very easy. कैसे होगा? Probability y less than equal to y is equal to the probability g of x less than equal to y is equal to the probability that x is less than equal to g inverse of y, which is equal to, this is the CDF of x. This is equal to fx of g inverse of y. और fx of g inverse y कहां से आएगा? जो x का PDF है उससे आ जाएगा. x के PDF को इंटीग्रेट करेंगे तो वहां से आपका ये x का CDF आ जाएगा, फिर आप उसको इवैल्यूएट कर सकते हैं. नाउ this is the CDF of y. This is fy of y. And differentiate इसको डिफरेंशिएट करेंगे तो आपके पास fy of y आ जाएगा, इसका डेरिवेटिव dy of this का fx of g inverse of y. G inverse of y. So that's how you will be able to calculate the PDF of y. Of course, example के बगैर गुजारा नहीं होगा. So example. So let's say you are given x is an exponential with parameter lambda. What that means is that fx of x is lambda e to the minus lambda x greater than 0. CDF of x इसको इंटीग्रेट करने से हमारे पास आएगा, that would be 1 minus e to the minus lambda x, also x greater than 0. That's the CDF. This is what we know. We already know about x. We already know everything about x. Now, I am interested in y, which is 2x plus 3. I am interested in asking a probability question about y. उसके लिए मुझे y का PDF चाहिए. What would be the PDF of y? So सबसे पहले fy of y is equal to the probability y is less than equal to y, which is equal to the probability 2x plus 3 is less than equal to y, which is equal to the probability x is less than equal to y minus 3 over 2. ठीक है, कुछ भी नहीं किया, सिर्फ थोड़ा सी जो है मैनिपुलेशन की है, y minus 3 over 2. But what is this guy? This guy is fx of x evaluated at y minus 3 over 2. But fx of x is this guy. So this would be equal to 1 minus e to the minus lambda y minus 3 over 2. This is the CDF of y. And of course, the condition is that y minus 3 over 2, which is this parameter here, has to be greater than 0. Has to be greater than 0. Which means that y has to be greater than 3. Y जो है 3 से बड़ा होना चाहिए. Now this is the CDF. How do I get the PDF? Differentiate. Differentiate. You will get the PDF, and that would be lambda over 2 e to the minus lambda y minus 3 over 2 for y is greater than 3. This is the PDF of y. This is the PDF of y. Using this, I can answer any probability question about y. Using this, I can answer any probability question about y. Now, what happens when you have a situation? When you have a situation कि यहाँ पे तो y की linear mapping है x के साथ. What about y is equal to x square? जहाँ पे linear mapping नहीं है. Two values of x will map to the same value of y. Two values of x will map to the same value of y. उस केस में क्या करेंगे? उस केस में ऐसे करेंगे कि again probability y is less than equal to y, which is the CDF of y, fy of y, CDF of y. This is equal to probability x square less than equal to y, which is equal to now x can be positive or negative random variable, positive or negative random variable. So this would be equal to probability minus square root of y less than equal to x less than equal to square root of y. As long as x is between minus square root of y and plus square root of y, we will have x square would be less than equal to y. So this is equal to fx of square root of y minus fx of minus square root of y. तो ये बेसिकली आपके पास ये डेंसिटी फंक्शन था x का, fx of x. एक जगह पे आपके पास square root of y आ रहा है और एक जगह पे minus square root of y आ रहा है. So I am interested in the probability that x is between minus square root of y and plus square root of y. So that would be equal to this blue area, ये सारा blue area, minus this red area, And the blue area is fx of square root of y, and the red area is fx of minus square root of y. अच्छा, अब इसको डिफरेंशिएट करते हैं. So fy of y differentiate from CDF to PDF, that would be equal to, अब इसका डेरिवेटिव क्या होता है? What is the derivative of x of square root of y? This would be CDF है, CDF का डेरिवेटिव PDF होना चाहिए. So this would be fx of square root of y. ठीक है? But hang on, it's not so easy because now it's square root of y. तो मुझे उसके साथ y का डेरिवेटिव मल्टीप्लाई करना पड़ेगा. So 1/2 square root of y का डेरिवेटिव is 2 square root of y in the denominator. Minus, इसके साथ भी ऐसे ही होगा. This would be fx of minus square root of y, और फिर minus square root of y का डेरिवेटिव क्या होगा? Minus 2 square root of y. और वो जो माइनस आएगा वो इसको प्लस कर देगा. So in general, this is true. In general, this is true that if if x1, x2 dot 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 are the solutions of g of x, y is equal to g of x. जैसे यहाँ पे आपके पास y is equal to x square था, उसके दो solutions थे, x is equal to plus square root of y and x is equal to minus square root of y. दो solutions थे, लेकिन दो से ज्यादा भी हो सकते हैं. So y can be a cubic equation of x. So फिर उसके अंदर जो है वो x के तीन solutions हो गए, तीन solutions हो गए. So if it has multiple solutions, ठीक है? If it has multiple solutions, then the PDF of y can be expressed in terms of PDF of x. Fy of y would be equal to summation I is equal to 1 to k. ये ऊपर भी देखेंगे हम, ये भी summation हुई है, ये दो की summation है क्योंकि हमारे पास दो ही रूट्स थे. यहाँ पे अगर k आपके पास रूट्स होंगे, यहाँ अगर आपके पास k रूट्स होंगे तो k रूट्स या k सॉल्यूशंस होंगे, तो हमारे पास ये k की समेशन होगी. कैसे? fx of xi जो यहाँ पे हमें नजर भी आ रही है, fx of plus square root of y or minus square root of y divided by the derivative divided by g prime of xi, g prime evaluated at xi and modulus of that. मॉडुलस इसलिए कि नेगेटिव वैल्यू जो होगी वो इस नेगेटिव के साथ मिलके पॉजिटिव होगी. ठीक है, या इसको ऐसे भी लिख सकते हैं, I is equal to 1 to k fx of xi d x over dy evaluated at x is equal to xi. Very quick example. And the example is x is uniform 0, 1, and y is equal to e to the power x. Okay. Find PDF of y. x का PDF दिया हुआ है, y का PDF मालूम करना है. ठीक है, तो पहले मैनुअली मालूम करते हैं, मैनुअली फिर हम ये बाद में फॉर्मूला लगाएंगे. मैनुअली इज fy of y is equal to probability y is less than equal to y is equal to the probability e to the power x is less than equal to y is equal to the probability x is less than equal to natural log of y. ये log मैंने जो लिखा है natural log of y, which is equal to fx of natural log of y. And what is the CDF of a uniform? The CDF of a uniform is just the value. CDF of fx of a is a. CDF of uniform. इसके लिए लिमिट्स भी कि लिमिट्स क्या होंगी कि 0 should be equal to log of y less than 1, which is equivalent to saying that y is between 1 and e. So this is the CDF of y, fy of y. Differentiate करें, you will get the PDF is equal to 1 over y under the same limits. PDF जो है हमारे पास y fy of y is equal to 1 over y. Okay, using formula use करते हैं, ये वाला. कितने रूट्स हैं इसमें कितने रूट्स हैं, कितने सॉल्यूशंस? y is equal to e to the power x, which means x is equal to log y. Just one root, एक ही रूट है, एक ही सॉल्यूशन है इसका, x is equal to log y. इसके अलावा और कोई सॉल्यूशन नहीं हो सकता. So आपके पास fy of y using this formula is summation I is equal to 1 to k. तो एक ही है तो इसमें summation की जरूरत ही नहीं है. So this would be equal to f of x of xi, and xi is log y, divided by so dy by dx evaluated at x is equal to log y. And what is dy by dx? Y is e power x, so dy by dx is also e power x. So this is equal to fx of log y. By the way, since this is uniform, so this should be equal to 1. यूनिफॉर्म है तो आपके पास यूनिफॉर्म 0 1 है तो वो 1 ही होता है। ये बिल्कुल इस तरह का पीडीएफ होगा, 0 और 1 के बीच में। यहाँ पे ऑब्वियसली log of y should be between 0 and 1, ठीक है। 1 divided by dy by dx, which is e to the power x, for x is equal to log of y. When x is equal to log of y, so this will turn out to be equal to 1 over e to the power log of y, which is equal to 1 over y. This is equal to 1 over y under these conditions, which is exactly the same as this. So चाहे formula से find out कर लें, sometimes it is easier to use the formula, sometimes it is easier to use the manual method. I am going to mention something जो आसिम ने अपने एक लेक्चर में मेंशन की थी, characteristic function. So we call this moment generating function. उसकी थोड़ी सी जनरलाइजेशन है characteristic function. उसकी जनरलाइजेशन है characteristic function. Moment generating function, as the name tells you, mx of t is defined as expected value of e to the power tx, where x is the random variable. Where x is the random variable. ये कहाँ पे काम आता है? ये हमारे पास काम आता है मोमेंट्स फाइंड करने में। मीन को फाइंड करेंगे, एक्सपेक्टेड वैल्यू ऑफ एक्स फाइंड करें, एक्सपेक्टेड वैल्यू ऑफ एक्स स्क्वायर फाइंड करें, एक्सपेक्टेड वैल्यू ऑफ एक्स क्यूब फाइंड करें, उसके लिए काम आता है, ठीक है। एंड द कैरेक्टरिस्टिक फंक्शन इज नथिंग बट द मोमेंट जनरेटिंग फंक्शन विद, यहाँ पे एक आई एक्स आपके पास और एक्स्ट्रा लग जाता है। एंड द रीजन फॉर दैट इज कि e to the i t x, this is limited, ये इनफाइनाइट नहीं हो सकता आपके, क्योंकि e to the power i t x इसकी मैक्स वैल्यू जो है वो 1 हो सकती है, ठीक है। बट e to the tx, which is the moment generating function, इसकी कोई भी बड़ी वैल्यू भी हो सकती है, बहुत बड़ी वैल्यू भी हो सकती है। क्यों यूज होता है मोमेंट जनरेटिंग फंक्शन? मोमेंट जनरेटिंग फंक्शन इज ऑब्टेन्ड फॉर मैनिपुलेशन ऑफ रैंडम वेरिएबल्स। 2 रैंडम वेरिएबल्स का सम करना है या 3 का सम करना है, उनके मोमेंट जनरेटिंग फंक्शन से बहुत इजी हो जाता है। सो मोमेंट जनरेटिंग फंक्शन इट ट्रांसफॉर्म्स द इंटीग्रल प्रॉब्लम। जब भी आपने इंटीग्रेशन करनी होती है उसको डेरिवेटिव प्रॉब्लम्स में जो है कन्वर्ट कर देता है। देयर आर अ फ्यू एग्जांपल्स व्हिच आर गिवन इन द नोट्स, टेक अ क्विक लुक एट दोस। वी आर नॉट गोइंग टू कवर द मोमेंट जनरेटिंग फंक्शन इन एक्सटेंसिवली हम नहीं कवर करेंगे, although कि हमने काफी सारी एग्जांपल्स जो है वो नोट्स के अंदर प्रोवाइड कर दी हैं। You will not be tested for the moment generating function in the quizzes as well. So moment generating function हम नहीं पूछेंगे, characteristic function भी नहीं पूछेंगे, ठीक है। तो किसी का क्वेश्चन आया? We previously said that for with large n, binomial is Poisson random variable. Binomial is Poisson random variable. That is true, but this is only half of the condition. Poisson random variable approximates a binomial for large n, but also for small p when n times p is moderate. Okay? So Poisson also starts looking like a normal. So in fact the working example, ये हमने कुछ example show की है, एक जहाँ पे जिस situation में it is very useful to use the normal approximation. So binomial को Poisson से भी approximate कर सकते हैं when n is large and p is small. Okay? And when n is large, irrespective of p, I can still use the normal distribution to approximate the binomial. Obviously for large n and small p, Poisson will approximate the binomial, normal will also approximate the binomial. That is true. So we cannot say that Poisson is normal, but the shape of the distributions, they look very similar for very large value of n. For very large value of n. Okay. So any other question before we close the session? Integration table? What do you, I'm not sure what integration table do you need? उस्मान, ये कौन से इंटीग्रेशन टेबल की बात कर रहे हैं? Z table. Not sure. Z table हम upload कर देंगे. Z table को upload कर देंगे LMS पे. That is not a problem. We'll upload the Z table on LMS. It's available in every probability book. Every probability book Z table आपके पास available होता है. But we will upload a copy on the LMS. ठीक है? Any other question? Okay, if there are no more questions, I will stop the sharing and close the session. We'll see you on Monday.